It's great to be here today, and I appreciate you taking the time out of your busy schedules to join us. We are Radiant Vision Systems, a world leader in light and color measurement, and we have been providing scientific-grade measurement solutions for nearly 25 years. We're excited today to share with you our latest advanced vision technologies with the goal of simplifying the most difficult assembly verification challenges. So today's presentation will cover a few topics: assembly verification challenges, the trouble with current methodology, what the solution is, INSPECT.assembly, application examples, system specifications, and then we'll have a summary at the end with questions and answers. So let's take a look at some of the really tough inspection problems. These problems are still, there's presence, position, and integrity of components. It's crucial for device function, but the greater number and broader diversity of details there are to verify in an assembly, the more challenging it becomes to inspect. Both humans and machines have difficulty parsing these details due to both the visual acuity, judgment, and consistency of the evaluation performance. Visual contrast is really the key contributor to the noticeability of details in assembly. In this image, there are a number of screws, and while a light screw on a dark surface may be easy to pick out, the dark screw on a dark surface is much easier to miss. In the latter case, the region of interest may look the same regardless if the screw is present or missing. Sometimes a defect doesn't cause an immediate part failure. Even if the device passes a functional test, a defect such as a loose connector may result in a latent failure after the device has been shipped. These type of defects may only be prevented by detecting very subtle deviations in the component's position, like a slightly angled connector that may not be fully attached. Latent device failures can also result when components are pinched or broken through repeated use of a device. This can happen when components aren't installed in the appropriate positions, or when the internal components are closed in the device housing. Misplaced components like misrouted cables may come into contact with other components unintentionally. Hinges may pinch a cable as a device is used, or a hot battery in contact with a cable may melt the plastic, causing a failure down the road. So why is it that current inspection methodologies can't accurately or adequately meet these challenges? It's the age-old battle of man versus machine. Both human inspectors and machine vision systems offer unique benefits for assembly verification. Humans have superior visual acuity and reasoning ability. However, they lack the automation benefits of machine vision systems, which process and store objective, quantifiable data that can be acted on autonomously. Neither method is ideal, but for manufacturers of assembly, of course, it comes down to what's my risk versus the actual cost. So in some cases, human visual inspection is required for evaluation processes, and this may be industry specified or just an internal process standard defined by an OEM or manufacturer. Reasons for this are that the end product is too high value or high risk to be left to automation. High value displays, consumer electronic surfaces, and injectable fluids or parenterals are good examples of these. In other areas, human inspection may still be employed simply because machine vision systems are unable to detect the level of detail required for the device function and quality. Humans offer visual acuity and contextual judgment that adapts quickly to new criteria, where machine vision systems lack imaging performance to see details and must be pre-programmed to recognize the unique areas of interest on a particular device under inspection. When test-to-test and line-to-line accuracy and consistency is critical, machine vision systems offer the benefit of repeatable, objective data. Of course, humans are not always reliable inspectors, and we as humans are prone to make assumptions to save time. So humans are also subject to physiological changes as a result of time of day. Is it break time? Is it after lunch? Is it before lunch? What's happening else in the rest of their lives? And any of these things could affect their mental state. Of course, all these factors cause subjectivity of inspection results from inspector to inspector, which makes the line-to-line accuracy impossible. In cases where a manufacturing process requires consistency through multiple stages of the line, across manufacturing locations, or between supplier and OEM, the consistent and objective data acquired by machines is critical. Quantifiable data is needed for interpretation by other machines on the line. While a human inspector may not be able to tell if a defect exists or not, and may be able to offer a subjective grade as to the severity of a defect, they are unable to provide a precise data point, which allows machines to act autonomously or manufacturers to improve processes over time. When data is quantified, exact tolerances can be set to initiate autonomous action when the tolerance is reached, such as the number of screws missing from a component, the exact distance of a cable from a battery, and this data can also be aggregated over time to show trends in defect scope, as well as severity that may indicate an issue in production. These data points can lead to improved process control over time and offers a point of reference in communication with vendors about component issues. It also enables the holy grail, the big data, where machines are able to share data across a wide network, enabling even more intricate autonomous processes. So how is this achieved? One important specification of imaging systems like machine vision cameras is resolution. In CCD imaging systems, higher resolution sensors enable easier detection of contrast variations, pixel level defect detection and correction, such as in a display device, and detection of subtle defects. Of course, resolution allows a camera to acquire finer detail within an image, like an exact distance, for example, between a connector and a connection point, or the precise alignment of a chip in an assembly. Another specification of imaging systems is dynamic range. This is the camera's ability to correctly interpret the meaningful data from an image among noise caused by imaging components and processes. So what is dynamic range? Dynamic range is all about contrast. The larger the dynamic range of an imager, the more grayscale values that the captured image will have. This combined with high resolution is critical for fine detail measurement, where resolution is the number of pixels captured, and the dynamic range is the amount of meaningful variation between the pixels. With a high resolution, broad dynamic range camera, machines can perform inspection with even better acuity than human vision, easily detecting whether cables that are routed below or on top of cable guides, or if a black screw is missing from a black surface. The last specification is really all about reducing system-level variability that may cause cameras to perform inconsistently within their imaging environment. First, the optimal electronics should reduce image noise as much as possible. Secondly, optics should be adjusted to the imaging environment. In advanced cameras, these variables are calibrated out, adapting the camera's electronic specifications for the most accurate images possible. Like humans, advanced calibrated cameras are adaptable to each imaging scenario, and it adjusts their perception based on where they are and what they're looking at. So it sounds like we just need the best machine vision camera out there, and we can achieve human-level inspection with data-driven results, right? Well, everyone who's evaluated a vision system knows that the camera is only the first step. Another problem with current inspection methods, even advanced machine vision systems, is that they need to be integrated. You have software, lighting, operator interface, some kind of fixturing, there's robotics potentially, and other equipment in order to function. So to perform the manufacturing requirements. These systems components are both costly to acquire and time-consuming to specify and assemble on the line. This is another failure of the machines, of course. While human inspectors offer imaging, processing, power, judgment, motion control, and other features all in one, a machine vision system requires some assembly. Even if a manufacturer is able to source the best camera, the best software, and the best fixturing, is it all compatible? Who installs it on the line? Does the integrator do it? Does the manufacturer do it? Does the integrator understand each system well enough to enable the best solution and provide the best support? Who's programming the software to do the job? Radiant offers a solution to these challenges in our INSPECT.assembly system. INSPECT.assembly is a fully integrated inspection station. It combines advanced imaging, comprehensive machine vision software, lighting, fixturing, the HMI or GUI, and automation for the best inspection capability available in a complete system that simply rolls up onto the production line. The key benefit of INSPECT.assembly is that it is a zero-hassle solution for any manufacturing challenge. Radiant has taken the burden of specifying, configuring, and integrating the optimal components in a complete turnkey system and pre-configures these components to meet exact assembly verification needs per each manufacturer per part under inspection. The components of an INSPECT.assembly system include advanced imaging through Radiant's Prometric Y29 imager, our custom configured INSPECT software, and all-inclusive fixturing that adjusts to fit any moving conveyor or test station. INSPECT.assembly is production line ready. It occupies the same footprint on the line as a human inspector. The system is designed for the assembly line with height adjustability from 525 millimeters to 950 millimeters to fit over any conveyor. Rotating wheels allow the system to be easily rolled up to the line. Internal components include camera, lighting, and triggering mechanism to capture images of the parts in an extremely high detail for inspection by the system software. The INSPECT.assembly is specifically engineered for assembly verification, and it performs many tasks such as component presence absence, testing of connectors, cable routing, presence of screws or absence of screws, batteries, labels in their location, fasteners, and other missing components. And of course it does all of this on a moving conveyor to ensure production lines keep moving. The INSPECT.assembly system leverages Radiant's advanced imaging capability. Radiant has built its business engineering cameras that combine the visual acuity of human inspectors with the objective data of automated machine vision systems. These systems replicate human visual perception of light and color and have been historically used to interpret subtle fluctuations of light that can indicate meaningful visual details in lit devices like displays and light sources. This example illustrates the difference in inspection performance between a standard machine vision system and the performance of the INSPECT.assembly's integrated imaging system from Radiant. While the typical machine vision system lacks the imaging capability to discern something like a black screw from a black surface, the advanced imaging system in the INSPECT.assembly correctly detects one missing screw using its combination of resolution and dynamic range. Radiant's advanced imagers outperform standard machine vision systems, offering a camera that inspects like a human. This is achieved through calibration to ensure absolute measurements in variable imaging environments, high resolution, low image noise, and broad dynamic range to capture the greatest, most precise amount of meaningful detail in images. These specifications allow the system to detect defects as good as and often better than human inspectors. Dynamic range enables fine detail measurements with consistency that beats human perception. And this precision enables Radiant's imagers to measure defects in terms of severity, comparing quantifiable data against program tolerances to ensure defects are evaluated in the context of the quality requirements. Compared with human inspectors, INSPECT.assembly can handle greater complexity than a human with consistent and objective results, all while gathering quantifiable data. INSPECT.assembly is faster and more reliable than human inspectors. This results in higher quality out the door and cost savings due to reduced labor. And finally, INSPECT.assembly can more reliably detect subtle defects that may result in latent failures, which incur cost and customer dissatisfaction. So for example, a device with a loose connector may pass functional test in the factory, but after shipment, the connector may detach, causing the device to fail and of course be returned or have an unhappy customer. Applying standard machine vision algorithm to detect this component does not allow us to determine the different features that indicate a defect. So, how is this issue resolved by Radiant's engineering team? In this example, a number of inspection algorithms are combined into machine vision super tools to ensure accurate detection of defects for this unique part. In this case, Radiant's engineers combined several algorithms to locate and analyze the screw and its shadow. These algorithms combined make up the screw tool, for example. Because Radiant owns all of the technology behind the INSPECT.assembly system, our engineers are able to program all aspects of the inspection criteria from the ground up. Our engineers define each software recipe based on actual customer parts for pre-deployment programming. Many recipes or multiple recipes are supported by an INSPECT.assembly system to handle new products on the line. Now let's take a look at some example applications performed by the INSPECT.assembly system. In these examples, we'll look at images taken by the INSPECT.assembly system and the precise component differences that are detected, indicating the defects. These images captured by INSPECT.assembly show the subtle differences that are detected that indicate errors in the cable routing, for example. These errors may not cause issues in functional testing, but may result in latent failures after the product ships. Small gaps such as 1 micron and part features that fall out of the area of interest due to misalignment between connectors and connections are also detected by the system before loose connections become misconnections. As we already saw, the INSPECT.assembly system uses various methods for detecting screw presence. Missing screws are not only an issue because components may become loose during device use, but also because a missing screw isn't a non-existent screw. Could the screw still be loose in the assembly somewhere, and what damage could this cause? While inspecting precision level components, the INSPECT.assembly system can also identify position and presence of other elements, such as labels, barcodes, logos, speakers, camera apertures, and more. So let's take a quick look at the basic steps performed by the INSPECT software. As the part passes below the system, the camera is triggered to capture the raw image. Through image processing, the system is able to register the image to provide a clear view of all components without rotation or distortion, with adequate contrast and cropped to the area of interest. The system software identifies regions of interest and determines component accuracy based on the pre-configured tolerances. To give you an idea of how this works in real time, let's take a look at the system in action. Great. So finally, I'd like to go over the specifications of this system as specified by our engineering team so that you can have the same important information that you need to make the specification. So here are the basic need-to-knows about the INSPECT.assembly system. So a typical workstation with Intel Core i7 is provided 32 gigabits RAM, 1 terabyte hard drive, Windows 10. Monitor is included, and camera, radiant imaging. The illumination also included, part and place sensor, so it could be an operator-driven trigger device, push button, and a smart camera-based triggering device. The software included is Radiance INSPECT software with INSPECT.assembly configuration. The test housing is a fixture size 1200 millimeters in height by 890 millimeters in depth. Installation time is required, so 2 days of on-site installation time is required for the software and hardware configuration with a Radiant engineer. And delivery schedule 4 weeks from receipt of a purchase order. So to summarize, what does the system do? INSPECT.assembly detects a variety of components present or missing, which are in full view and contrast with background. The system is capable of aligning with the part to proper coordinates if fully within the field of view. Unique alignment features across all product families are required. And once the first registration occurs, fine registration locates features within the part to micro-position the FOIs or features of interest for individual component tests. Inspection results are reported to the UI or user interface and optional separate operator monitor screen. Results for failed panels are archived to individual XML format files, which could include serial number or any other time, date stamp features of the list that failed. The system detects changing components and performs the correct test. In general, specified is a minimum 50% luminance change between components, and all the components need to be tested and registered before the production run. We have the ability to distinguish different model and mixed product using either the smart image sensor or features within the inspection test image itself. Based on the complexity of decision making, additional cycle time could be required. There is a network option for communicating pass-fail or test data and product information with the planned network. An optional barcode reader allows matching the test data with a specific unit and checking the model information. There is a minimum of 2 pixels per narrow bar width with a minimum of 30% contrast. We can also provide a duplicate second monitor display, which could be placed remotely on the manufacturing line. And this, of course, would allow for simultaneous viewing of current part results. So some additional options include different working distance or field of view. So we offer 35 millimeter lens or 50 millimeter lens options. And we can increase or decrease the field of view plus or minus 15%. Of course, in order to develop a system that accurately meets your needs, there are a couple things we need. First off, we need some part samples. So we ask that our customers provide a range of part samples 10 days or a minimum of 10 days before the factory installation. Each model or revision of the part just needs 10 good samples and 10 samples of each failure mode. We need to then make sure or determine that the line speed is appropriate. So the maximum line speed that we're going to be operating under is basically half a foot per second. There is a minimum indexing time, which is typically 5 seconds from part to part. We do need space on the line, of course, so the system requires 1200 millimeters in height and more or less 700 millimeters in width. And the minimum line height should be 525 millimeters with the maximum line height up to 950 millimeters. And the depth is 700 millimeters. For barcode reading, if it's required, the barcode location should be consistently positioned and unobstructed. For product and model mixing, up to 4 of similar part variations per line for adequate product model mix. The component mix per part would be associated to second sourcing. And essentially, our engineering group just needs to see some samples of what the second sourcing could look like for evaluation. There is quite a bit of mix that's allowed for this, but there is a requirement that there be a distinct luminance change between the components, and we just need to know that beforehand. So in summary, human inspectors and machine vision systems have unique advantages and disadvantages for visual inspection, and neither offers the ideal solution. Advanced imaging systems from Radiant Vision Systems combine human visual acuity with consistent, quantifiable data acquired by machines for true automation. And INSPECT.assembly integrates this advanced imaging with specially configured software and fixturing into an inspection station that easily rolls up to your existing lines.
All right. Great. Thank you, Davis, very much for that presentation. Thank you all for coming to the presentation and sticking with us to the end here. If you need to leave for any reason, please feel free and always email us at info@radiantvs.com if you have questions that you weren't able to ask today. But we are moving into our question and answer session now with Davis, so feel free to look over to the right side of your screen for that GoToWebinar interface and find the questions window where you can send us a question, which we will read now. And I see there's a few questions in here, so I'm going to turn things back over to Davis to answer some of these questions in the queue.
Okay, so here's a question. Can the system be used with other inspection software? I think what that means is some third-party source software using Radiant's cameras, I believe is what the question is asking. And in this case, the answer is no. Radiant is using, well, proprietary. So Radiant cameras are only working with Radiant software and vice versa. Okay, next question. Does the system detect new parts as they enter the line, or does this change need to be programmed? Okay, good question. Yeah. So it could be that, well, okay. So let's start off this way. We do need to know what the model is that's coming. So that would be something that's pre-programmed. But the INSPECT.assembly system can handle multiple parts coming through at different times. So it would be able to trigger it and inspect that even if there was a mix of product on the production line. Hopefully that answers that question. How is data communicated to the factory or network? Yeah, okay. So because we're providing a PC with the system, essentially however you want to communicate from the PC, you would be able to do so. So whether that's through networking, some Ethernet or serial communication, any of that could be available through the PC device itself. Sorry, there's a question about specs, so let me just pull my spec sheet and make sure that I answer this one properly. Here we go. Okay, so the question is, what is the maximum width of product that could be inspected in a single pass with the system? And so the max field of view, and it's not exactly square, so it's is going to be 600 millimeters by 400 millimeters. Okay, so the question was, could it be up to 890 millimeters? Yeah, so not quite that big, 600 millimeters by 400 millimeters. Good question. Okay. Okay, what is the process for getting a system configured and how long does it take? So in general, what we expect is 2 days on site. But what is the process for getting a system configured? Fairly straightforward. Essentially, one of our sales engineers would be in contact with you. We'd ask for some samples. So we need a few good samples. We need a few bad. So in general, we like to see 10 of the good and then 10 of the bad. So we have that with our radiant engineers, and they configure based off of that. We do the evaluation on the front side to confirm that everybody's happy with the results that we saw for. And then from an installation standpoint, 2 days. So deliver the system on site to the customer's location, and then 2 days to get things tidied up and ready to run. Okay. Since the system uses cameras for light measurements, could it be used to look at assemblies with lighted components as well? Yeah, okay, good question. Yes, absolutely. Okay, looks like we just had another question come in about line speed. So what is the, where did it go? What is the maximum line speed with the system? Good question. Yeah, so 12 parts per minute is the maximum. What other questions? Any other questions coming up? Okay, one more question. Last question. Okay. Can the system track parts by the serial number or other identifier? Yeah. So yeah, good question. So with the optional barcode reader, we could use that as the input, and we could dial that in from an output standpoint to track the pass-fail criteria to that specific serial number of the part.
Cool. All right, guys, it looks like questions are winding down here on the webinar, so we're gonna wrap this up. Again, if you have any other questions you think of later or something you didn't get a chance to ask, please feel free to contact us at info@radiantvs.com, and we will answer those questions for you there. Really appreciate your guys' time today joining us for the webinar, and we look forward to seeing you back at the next one. Thanks so much, and have a great day.